Should be fine. Okay, so we've busted out the variables here. So, because we're trying to find a basis for S on problem 4. So, is this my basis?
No.
How do we write the answer, is the question.
Brackets.
The set, right? You have to write it as a set. So, the basis is equal to the set of 2, 0, 0, 0, comma, negative 1, 1, negative 3, 0. That's it. A basis is a list of vectors that span the whole space. So you'll see that everything in S is indeed spanned by these two things. Now you've got to be careful. I don't want to, I see some people try to put the word span there. But when you're writing down a basis, you don't want to put the word span there, because if you write the word span there, you're not giving me a basis, you're giving me the entire space S, right? I just want the basis, so I don't want the span of that set.
Isn't a basis and span pretty much the same thing?
No, a basis is a small list of vectors, like this is a list of 2 vectors. The span of a set of vectors is all of the linear combinations of those vectors, which is a huge, potentially huge vector space. It's much more than just the...
Would span be like 2, 0, 0 plus B?
Right, this thing right here, this expression, this is what the span of these 2 vectors is. And what is this? This is a linear combination that represents an arbitrary element of S. So the span of the basis is the whole space, the whole vector space.
Where A
In this
and
case,
3 variables or something.
A and B are arbitrary constants, free variables, whatever you want to call them. Yeah. Okay, so what's the dimension of this space?
2.
Yeah. That's like the easiest question. The dimension is 2.
Let's say that.
Okay, everybody good with that?
So that's 10 out of 12 points to get dimension.
Something like that.
Okay. 98 over 100%.
Let's see. Okay, let's try a slightly harder one. Kevin?
To show work for this problem, could you just take the span that the span of those vectors is a subspace? Because isn't the span of any set of vectors always a subspace?
Oh, so what Kevin wants to do is he wants to do part B first and say that S is equal to the span of these 2 things, and therefore S is a subspace. Don't have to check closure under addition and scalar multiplication. If your set S is already represented as the span of something, it is a subspace. I think that came up on one of my test questions. The space was span of blah, 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 right? And people were wondering, is that a subspace? I'm like, yes, it is. It's the span of something. Right? Anytime you have the span of something, I don't care what it is a subspace by the very nature of it.
So for this problem, it would work for that.
Yeah, you could actually get away with that. I mean, the way that I force you away from that is one of 2 ways. I either say verify that S is closed under addition and scalar multiplication if I really want you to do that, or I put you in a problem where it's not easy to see what the spanning set is. See, here it's very easy to see what the spanning set actually is, but it's not always so simple to just see it off the top. But that's a very good point. Did everybody follow that? If your set is the span of something, then there's no doubt it has to be a subspace. Yeah. Now, here's a question. I'll get to you in a second. Here's a question. So let's say that you realize that the set S is the span of something, and the something is 3 vectors. Does that make the space S 3-dimensional?
No.
Definitely not, right? So for example, if I tell you that S is equal to the span of 1, 1, 1, 1 and 2, 2, 2, 2, right? You say, yeah, S is a subspace, no question about it, and it's spanned by these 2 guys, right? But we wouldn't want to say that this is 2-dimensional, right? Because these 2 vectors do not form a basis for S on account of, I mean, they do span S. They are halfway to being a basis. Because obviously S is defined to be the span of those vectors, so by default, those vectors do span S, but they are not Li, as you can see. In this case, they are clearly LD because they're multiples of each other, but keep in mind it may not be obvious. It may not be as obvious as this example. You may have a list of vectors that maybe your best guess is they do look sort of Li, but you really do need to check that. You really would need to take those vectors. You know how to check that vectors are Li, right? I mean, when we're talking about functions, you use the Wronskian. But in the earlier material, you would put those vectors into the columns of a matrix, right? Row reduce it and see whether you had any free variables. Brandon?
If we had a question like that, we just jump straight into putting into the columns of the matrix, right? We don't have to like list like, okay, it's gonna be like a linear combination.
No, but you should explain to me what you're doing.
Oh,
Like you should explain somewhere along the line that you're checking these
Oh.
vectors for being Li or LD. Yeah. Actually, Juan, you had a question.
Can you just repeat what? So the span is the whole space of the vector space that we're talking about?
Right, the span of this set is the entire vector space.
You're looking to find C1 equals C2 equals 0. That's one.
Priscilla?
Why
But
is
that's
the
what you're saying,
dimension of
you're
x
looking
two?
for
Of this one?
before you put-
Because there's two vectors that are in the basis.
Oh,
Now the dimension of M2 of R, of course, is 4. The whole 2 by 2 matrices. We're not looking at all 2 by 2 matrices here. Only some of them, right? We're only looking at some of the 2 by 2 matrices, not all of them. So we have a 2-dimensional subspace of the 4-dimensional vector space of all 2 by 2 matrices.
You get the,
Right?
okay, you get the dimension of M2 of R, that's, you square that, right? The R value?
Yeah. Oh, yeah. So
That value?
right. So I guess this is another thing that could go on your flashcard for under your pillow at night, or something you need to memorize, which is some of those basic dimensions. So the dimension of Mn of R is n squared. I would expect everybody to know that cold and to know a basis for Mn of R, a standard easy basis for it, which would be a collection of matrices where you had all zeros but 1, 1, and the 1, 1 would move around each slot of the matrix. And you can see that this n by n matrix has n squared entries in it, and that's where that dimension comes from. That okay? Okay. Good questions. Let me move on. There might be some more questions that come up when we do this next example. I'm going to do problem number 2 off of the review sheet, which is closely related to the one we just did. So number 2, it says let S equal the set A plus BX plus CX squared plus DX cubed such that A plus C minus 3D is equal to 0. A plus C minus 3D is equal to 0. And we're going to do the same thing we did on the last example. We're going to show that S is a subspace. So show S is a subspace. Okay. So, anybody?
Subspace of.
Oh, it's, yeah, it's a good point. Subspace of P3 of R. Incidentally, while we're thinking about dimensions, can somebody remind me what is the dimension of Pn of R?
N plus 1.
Good. N plus 1 is the right answer. Okay, good. Okay, so this one I think is maybe a little trickier. The reason that I think that this problem is slightly trickier than the last one is that on this example, the form of the vector was already right in front of you, handed to you. Here, it's not really so true because it was given to you kind of as an arbitrary cubic polynomial, and then the condition was kind of extracted out on the side. Right? So if I want to start doing, I'm going to do closure under addition again. When I want to start doing this, it's going to be a little bit trickier. So let's just start off kind of casual with 2 polynomials. So I'm going to say let P of x, comma, Q of x be elements of S. So that's kind of just following the same format that we had used in the matrix example. Okay. Now the next thing that we did in the last example was we wrote out the format for what P of x and Q of x look like. Right? For what they look like. So how would you want me to write P of X here?
The same way it's written up there.
Just like this here?
Yeah.
Okay, so A plus BX plus CX squared plus DX cubed. Okay?
Can you just do A1?
Sorry, go ahead.
For Q of X, could you just put A1 instead of?
You can, exactly, so you have another polynomial for Q of X?
Yeah, just A1 plus B1X plus C1X squared, and then so on.
Okay, sure. Okay, so we certainly could do this, B in S, just like that. Right? So let me show you what people often do with this that we don't want to do because it's going to shortcut the work that we need to do. Here's what I see a lot of people do now. So don't write this down yet. People will write P of X plus Q of X equals A plus A1 plus B plus B1 X plus C plus C1 X squared plus D plus D1 X cubed, element of S, and we go home. Right? So, don't write that line down because I'm going to erase it in a second. So the question is, what is wrong with that?
You're missing
I skipped too far in what sense, Doug?
You didn't put the P of X and Q of X written out individually and then you combine the variables.
Well, okay, so you wanted me to do one more step where I wrote this one and then plus this one?
Yeah.
I could have done that. I still wouldn't have been happy with this. Yeah. What would I not be happy about? Gabby?
There's the additional A plus B minus 3B.
Yeah, we are not using this at all, right? And what we're doing, if we just show this, you know what you're actually showing? You're showing that P3 of R is closed under addition. That I am not interested in proving in this problem. I am trying to show that S is closed under addition. But when we just take arbitrary polynomials A plus BX plus CX squared plus DX cubed and add two of those together and show that we get something else that looks like the same form as a cubic polynomial, we are not showing that S is closed under addition. We are showing that P3 of R is closed under addition. This will get very, very, very little partial credit. This is way, way short because you're completely missing the point. This condition here has to be part of it. So I'm going to erase this line, and I'm going to go back, and I'm going to say, okay, write P of X equals this, Q of X equals this, B and S, and I'm going to say, thus, A plus C minus 3D is 0, and A1 plus C1 minus 3D1 is 0. We really do need to say that. So we're putting in the conditions here. Then, when we actually go to add P of X and Q of X together, P of X plus Q of X, what we can say is, all right, we can just still get what we got before, A plus A1, A plus A1 plus B plus B1X plus C plus C1 X squared plus D plus D1 X cubed. But before I just write element of S here, I should look back and say, well, is it really an element of S? What does it take to be an element of S? My constant term plus my X squared term minus 3 times my X cubed term must cancel out. So let's note, you'd have to put this in there, let's note that my constant term, which is A plus A1, plus my X squared term, which is C plus C1, minus 3 times my X cubed term, which is D plus D, where did that from? D plus D1, I would need to note that that is equal to 0. Is it equal to 0? Well, if you just rearrange, see, you've got these conditions. So if you look at this, this can be rewritten as A plus C plus, minus 3D plus A1 plus C1 minus 3D1. And that is 0 plus 0, which is equal to 0. Based on this note, which would have to be there, we could then say P of x plus Q of x is an element of S. Okay? So thus, P of x plus Q of x is an element of S. You have to address the condition. If you're ignoring the condition and you're just working with a polynomial of this form, you're really just working in P3 of R, you're not working in the set S itself. Yeah, Doug?
Can you do it where you have the P of x and Q of x and you write out the whole thing, and then do the such that, and then you write what your note says, because, yeah, because you'd have the main equation such that this equals that, which equals 0, or is that skipping too much?
So you want to just, so you're trying to do basically the same
Kind of, you
solution?
have what you have where you started, and then such that equals the note equals 0.
Oh, just say such that this equals this.
Basically skip the P of x plus Q of x.
And then having to like separate
That's fine.
Okay.
Yeah, that's actually okay. I don't even really need to see this separated. You could just basically tell me that this is equal to 0.
Okay.
Okay. Now, guys, in case you don't like that, there is another way to do this. Go ahead, Jake.
Can you substitute negative c
Oh.
plus 3d in the equation?
Okay, yes, that's what I was about to get to. Is that what you were going to say too, Gabby? Okay. All right, let me show you something else. I'm perfectly happy with that verification right there now, because I've incorporated the condition, but there is another way to do it that maybe you would prefer. I don't necessarily have a preference. But there is another way, which is that instead of writing P of x, instead of writing P of x and Q of x as being extremely arbitrary as cubic polynomials, you could write them so that they already incorporate the requirement here from the get-go. So an alternative here, I'm still talking about closure under addition. An alternative would be to simply say, let P of x equal, and then where you have A, you just notice that A is the same as negative C plus 3D. You guys see that? A is equal to negative C plus 3D. So you can literally just put that in for A, and then you've already made your polynomial a member of S without having to attach this extra condition along the side. So let me write down what that looks like. Negative C, actually you're going to prefer this one.
Yeah, still recording.
Okay, great. You're going to prefer this format, and you'll see why in a minute. This is the better way to do it, actually. So I say alternative. Let's say better alternative. You'll see why. So there's my constant term, and then plus bx plus cx squared plus dx cubed. See, now I can just say element of S right away. Okay, but before I do that, I'm also going to bring in q of x. Q of x is negative c1 plus 3d1 plus b1x plus c1x squared plus d1x cubed, element of S. I'm just going to take, basically I'm going to take the condition and incorporate it into the form of P and Q. Did you have a question, someone? Okay. Did somebody have a hand up that I missed? Now, yeah.
Does it matter if you put in for A and C or B?
No.
I know this is confusing,
You could solve for any one of the variables. However, I do tend to like to think of this as a system. Here's A. There is no B term. There's a C term of 1, and then a D term of negative 3, and augmented with 0. So I view the A as the free variable. So if we were doing this using free variables, kind of solving it like chapter 2, we would leave C and D as kind of the free variables, and we would solve for A in terms of the free variables. So it makes more sense to me to solve for A, which we've already done easily, but you technically could solve for any of them that you want.
Can you explain again why solving for A in this case, or just let you just write at the end element of S? Like I still don't get that.
Okay, it's because as soon as I have put my polynomial in this form, Brandon, then it's already in S. So what does it take for something to be in S? Constant term plus x squared term minus 3 times x cubed term must be 0. You see that that's true for the p of x that we have over there now?
Oh, I see it.
Constant term, take this, add this, subtract 3 times this, you get 0. So it's in S.
But you're not subtracting the 3D from here, because wouldn't it have to be minus 3D?
Well, no. This is my constant term. This is like the A term. This is the C term. I'm subtracting the 3 over here. So you subtract 3 times whatever this is,
And then you get
which
it.
happens to cancel out what's right there.
Okay. Okay.
Okay. And then of course the same thing on the second line. You know why I'm going to prefer this version over the first version? Does anybody know why?
Minus basis.
The basis and dimension part of it, which is part B of the question, which we're not even getting to yet. I mean, how do we find a basis? We're going to bust out the variables, right? Well, if you bust out the variables over here, if you bust out the variables here, you're going to tell me that the basis is this. Because that's what you get when you bust out A, B, C, and D. Well, that's not the right answer. Right? But if you bust out the variables over here, bust out the B, bust out the C, and bust out the D, you'll get 3 polynomials. It's a 3-dimensional vector space. Okay. So anyway, I'll come back to that point in a second. Once you've written this down, then P of x plus Q of x is just, now you just literally add these things together. So vertically, so negative of C plus C1 plus 3 times D plus D1, and then plus B plus B1 x plus C plus C1 x squared plus D plus D1 x cubed. What you need to do is you need to write that down. Trust that the math is going to be there to support it. You write that down and then you check. Is this in S? Well, what does it take? The constant term plus this term minus 3 times this term has to be 0. That's the condition. Is it true? All of this plus this minus 3 times this. What do you get?
0.
You get 0, which is exactly what you were required to get for this thing to be an element of S. So now you just simply say element of S. You don't have to have any notes on the side like we did over here if you do it this way. You can just go straight to that. Okay? The main thing is, guys, be sure that you are incorporating the condition. The A plus C minus 3D equals 0. It is so tempting, I see it so often, that people approach the problem this way. Technically, this is fine. You can do this, and then you just add P plus Q, and it's the easiest thing in the world. But you somehow have ignored the condition, though, right? So you have to put in this extra stuff about the condition as you go along if you approach it this way. Whereas if you approach it this way, you're putting the condition in right away when you even write down the form of P of x and Q of x. Yeah. Okay, and then the scalar multiplication is similar. Would you guys like me to show it to you, or are you okay without that part?
How would you do it?
Yeah.
You want to do it? All right, we'll do it real quick. Okay, so closure under scalar multiplication. I'm going to do it from this perspective here. So I'm going to say let P of x be as above. And what else am I going to do? K is an element of the real numbers. Good. Okay, so then I just take K times P of x. And that means I'm taking K times this first polynomial here. So that's just going to be K times negative C plus 3D plus KBX plus KCX squared plus KDX cubed. And I just look at that, and you could multiply this out right here if you want to, but I would be okay with you just simply looking at it and telling me that this constant term plus this x squared term minus 3 times this x cubed term adds up to 0. Doing that in your head is fine, and therefore it's an element of S. Sergio?
So if we were to do it that way, we would have to do the same thing, say note if K.
Yeah,
times
if we did it this way, yeah, so I don't like this way quite as well. If we did it this way, we'd have to take K times, A plus BX plus CX squared plus DX cubed. We would get KA plus KBX plus KCX squared plus KDX cubed, and we would not want to just say element of S with no explanation. We would have to stop and say, note that Ka plus Kc minus 3Kd is 0. And the reason that this is 0, of course, is that after you factor the K out of it, you just get that, which is already 0. So, okay, yeah, Zach?
Before you really wanted us to distribute the K into the parentheses, does it not matter as much in this case?
That's not that it doesn't matter, it's just I'm being a little lazy.
Oh, okay.
Just the circled part plus this part minus 3 times this part is 0. I can see that in my head easily enough. Okay, so so this thing is a subspace, and now if we want to get a basis, I think this is part B of the question. I think I'll squeeze it right down here. How am I going to get a basis for this? Bust out the variables of which form of P of X? This one up here, right? Not the one way over there, with just the general A plus BX plus CX cubed plus DX cubed. We just want to use this one. So we'll bust out the B. When I bust out the B, what do I get? X, right? When I bust out the C, what do I get? Negative 1 plus x squared. When I bust out the D, what do I get? 3 plus x cubed. Okay, and what's the dimension? How many things do I have here? 3, right? Actually, before we jump to that conclusion so quickly, let me just ask another question. There's 3 things in this list here. Okay, so this is a base. Okay, so we believe this is a basis, right? Can somebody just give me a little quick snippet about why it's a linearly independent set? Because I'd like to know.
They're not three-dimensional.
Okay, let me slow down. I heard several things there. The first thing is when you're talking about vectors being multiples of each other or not, when you have only 2 vectors, that's a really great trick to say, well, if they're not multiples of each other, then they must be Li. However, when you have 3 vectors or more vectors, just because they are not multiples of each other doesn't make them Li. The best example of that I have memorized by now after teaching in class 15 times is it turns out the vector 1, 2, 3, 4, 5, 6, and 7, 8, 9, they are LD. But none of those 3 are multiples of each other. Okay? So you can't tell me, oh, these aren't multiples of each other, therefore they are linearly independent. Right, you have to give me another something else. Oh, somebody wants to use the Wronskian. That's actually a great idea. That works. You can use the Wronskian. These are functions. These are like calculus functions. They could be seen in chapter 6, and it would make perfect sense. We can put them in the top row of a matrix, take enough derivatives so that it's so that it becomes a square matrix. Just a second, Doug. Okay, so I'm gonna mention, so why are these linearly independent? That's kind of a good point. So there's many answers we could give. One of which I really like is this Wronskian idea. So we could just take the Wronskian of x and negative 1 plus x squared and 3 plus x cubed. We could literally just take that Wronskian, and what we would get would be the determinant of